Okay, so I am sending you this video because I am trapped on an alien planet. And no, so we're going to be talking about motor sizing and configuration. I'm going to try to keep this video short. Oh, great. Of course, this is going to zoom in and out all video long, isn't it? Fantastic. Let's hope it doesn't. We'll see. Let's hope that this isn't nauseating. No promises. All right, so let's talk about motor sizing. So when I do motor calculations, typically I always start by assuming that a vehicle is traveling up a 20-degree incline. Okay, 20-degree incline means that this vehicle is assumed to be traveling at a constant rate up this 20-degree incline. Wow, this is so bad. I need to fix my frame rate. We may just have to zoom out a bit. Wow. It's just not giving me what I want. Oh well. Boy, that's terrible. I wish I knew more about cameras, because I really don't know enough to be able to fix some of this sometimes. Let me see if I can change the shutter rate. I think that's the problem. There we go. All right, we'll see if that fixes the problem or if it just makes it a different kind of bad. So far, so good. Okay. So we're going to assume that this vehicle is traveling on a 20-degree incline. Okay, which means if we do a sum of the forces on this vehicle, you have a normal force, Fn, you have a friction force, Fr, that is the friction that's being exerted by the wheels that's pulling it up the incline, and then you have the gravitational force, Fg, okay? This gravitational force is located 20 degrees opposite of where we're going to mount our x prime and y prime axes. So x is going to be at an incline 20 degrees, y is going to be at an incline 20 degrees this way. Okay, now we don't really care about what the Fn value is. We're going to assume that the vehicle is heavy enough that it actually is capable of propelling itself. So we're not going to focus on the Fn value, we're only going to focus on FFR. Now at steady state, FFR is going to be equal to Fg sine 20 degrees. Okay, so whatever your Fg value is, that's important. Now your FFR, your friction force, this is the force that's actually being put into the wheel by the motor itself. If you have a 1-to-1 gear ratio, that means that FFR is equal to the torque of your motor multiplied by the radius of your wheel. Okay. Now, when Guy and I did these calculations, we kind of did it this way, where we start with force and we figure out how much torque we're going to need. The other side of this that we're going to have to calculate is your speed. So here, you know that you have a certain velocity, a nominal velocity that we're going to design for. I think of the calculations we did earlier, it was 5 miles per hour. 5 miles per hour in kilometers per hour. We'll operate in metric units because this is when we did all of our calculations earlier. is about 8 kilometers per hour, which is approximately 2.235 meters per second. Okay, so that's going to be our nominal speed. You can have whatever nominal speed you want. You can change this value. Now we know that the omega value for the wheel spinning is going to be equal to V divided by R. Okay, with our R value equaling 6 inches, which I'm going to calculate that in meters. Is 0.1524 meters. With that known and this known, we can then calculate what our omega is. And this is going to be given in radians per second. Yeah, this was an M for meters. So we'll divide 2.2354 divided by 0.1524, and we get omega is going to be equal to 14.665 radians per second. Okay, now we can do a conversion to how fast it's spinning in RPM. RPM is going to be equal to omega multiplied by how many. So here we've got 14.665 radians per second. We know that there are 2 pi radians in 1 revolution, and then we know that there are 60 seconds in 1 minute. So if we do that math, then we get 140 RPM nominal. Okay, so that's going to be the speed that we want. You can have a higher speed than that. You're going to want a higher speed than that, but we'll need these values, this one and this one, for some later calculations. So let's go back to this for a second. Here's how much torque we need out of the wheel. We right now know what the friction value is, so we can calculate T is equal to the friction value over R. Right now this is assuming only 1 motor. If you're going to have 2 motors, 1 on each side, you could divide this number by 2. So the force of friction is equal to this multiplied by number of motors. Okay, and so that ends up being number of motors is down here. Okay, so if you have 2 motors, it'll be R times 2. It'll reduce your torque by 1/2. Okay, so that's where we're at here. We already have this value that you can calculate by the weight of it multiplied by sine of 20 degrees. Radius of the wheel, which we have at 0.1524 meters, and the number that'll give you what your nominal torque is. Okay, so that'll be the amount of torque that's needed for this to maintain a constant speed as it drives up the incline. Okay, that's the torque value. Here we already have this, which is based off of our nominal speed. We're designing for, we want this thing to be traveling at 5 miles an hour up the incline, which means we have an angular speed of 14.665 radians per second, or 140 RPM. Okay, that's our nominal conditions. Now, when we look at the graph of torque versus speed for a motor, your graph is going to look something like this. Okay, you'll have some cutoff torque and some cutoff speed. This is the maximum speed, this is the no torque speed, and then this is the no crank torque. And everything will sit in the middle. Your optimum power efficiency, oftentimes, if we're talking about efficiency versus power, oftentimes you're going to have a bell curve that looks something like this, where the peak efficiency of your motor is really close to the maximum power that your motor is consuming. So what we're going to say is we're going to try to operate at peak power for this. Now if we were to draw in a power curve, the power curve for whatever power is selected is going to look something like this. Okay. What happens is at 0 speed, according to the power curve, you should have infinite power, but that's not possible. So this is kind of an idealized power curve based on if this is a 15 kilowatt motor or a 20 kilowatt motor. But in between here, this is the actual power that's required by the motor, and this is the power that's produced by the motor. So it's kind of the difference between how much power it's consuming versus how much power it's producing, that kind of thing. We never actually deal with this end of the curve or this end of the curve. We're only dealing with this part in the middle. Now we have a point that is about right here. We want it to operate near the maximum power. So what we have is for motor power, it's going to be equal to omega times T. Now T will have to be in units of Newton meters, and omega will have to be in units of radians per second. So you get a Newton meter per second. That is your power unit. That's a watt. Okay, so you'll need to know what that value is for your power of your motor. Now this is what I'm going to start calling a power output. This is what you need for the output power of the motor. Now if a motor was 100% efficient, your efficiency was 100%, then your output power would be equal to your input power. But as we can see here, this efficiency graph, it is not perfect. It's not 100%. 100% is close to about up here. The most efficiency we can get out of electric motors, I think we've seen some that get like 96% efficient. Under certain conditions, they have to be at a certain speed and a certain torque. Typically what I expect out of these though is somewhere between 60 to 80% efficient. If you operate off of an 80% efficiency expectation, usually that's good enough. And that's what I'm going to do. So here we're going to expect efficiency. We're going to expect that we're probably going to be at one of those 2 points on this efficiency curve, just because it's really difficult to always be in that center point. It would require some very precise gearing in order to make that happen. And you'd have to change your nominal values. And we're not doing that. So we know what the power output is. So to find the power input is going to be equal to power out divided by the motor efficiency. Here we're assuming the motor efficiency is about 0.8. So whatever this is, divide it by 0.8 and you'll find what your power in value is. And this is going to be in watts, is going to be your rated motor power. Okay, so that's kind of the calculations of how to reverse engineer this to find how much power your motor needs. Now, when you pick a motor, it's going to have at least this much power, at least. So if we go to picking a motor, I'm going to go ahead and erase this part up here. Some of the guidelines you have: motor selection. First of all, you want to make sure that the motor power that's rated on there is greater than or equal to P input that you calculated. Okay, that's first thing. Second, ensure that your motor velocity, motor speed, which is the no torque motor speed, is greater than or equal to your RPM value that we calculated down here. Okay, and then the third step is you've got to ensure that your no crank torque has got to be greater than or equal to this torque value that we calculated over here. Now ideally all three of these would be greater, hopefully. But those are the three checks that you need to make. If a motor you select beats all three of those criteria, that is a good motor for your application. Okay? So that's kind of Cale's quick and dirty calculation method for sizing motors for vehicles. Okay. Now we'll go into the next piece, which is steering. Steering is kind of interesting because when we talk about steering, there's a couple of different ways of doing this. If you have two different motors controlling two different sides of a vehicle, which is what I have for my little Rover robot that's here in my office, your vehicle will look something like this. And here, this is not a single axis, it's actually a broken axle. Each of these are independent axles. So this would be for a two motor spin. First of all, one option to do it is to link together these two axles, oftentimes with a chain. They'll spin at the same speed. Usually you would only do this if you're trying to build a four-wheeler off-road type vehicle. And that's just because four-wheeler off-road type vehicle, every single one of those wheels is going to need a certain amount of torque. Boy, my camera is just blurry. Good job, me. I'm not sure how long that it's been that blurry. I wonder if I can turn it. Have it look at me better. Well, that doesn't help. Nice. Well, it's working for now. Okay, so you can connect those two axles. Typically, again, I would say that's only for an off-road vehicle. You're not going to want to have four-wheel drive on a race car, or even on just a regular moving vehicle. So what you'll have is you'll have a motor, which is connected to gearing, connected to this axle. It's a motor 1 and motor 2. Okay. So let me talk about how to steer in a two-motor system. So your steering is going to occur due to the relative speed of the two sides. Okay, so if you think about it, if you are traveling along an arc, you're just turning, your outside wheels will actually be traveling faster than your inside wheels. Okay, your inside wheels just move slower. And you can calculate this based on the radius of curvature for both of these. Here, your rho value is going to be equal to like v squared over, whoop, that's wrong. Here, your angular velocity as you travel through this is equal to v over r. Okay, and here, both of these sides are going to have an equivalent omega because you're traveling around the same point at the same rate. So you have a V1 R1 is equal to V2 over R2. Okay, and your R2 minus R1 is going to be equal to your wheel width, which is this distance here between the center lines of your two wheel sets. Okay, so R2 minus R1 is your wheel width. That one you probably have already designed. So the question is, how do you control V1, V2? Well, V1 and V2 are given to you by the actual speed of the vehicle. Here, omega is the speed around this turn. It's not the speed of the individual motor. V1 and V2 can be given by omega 1 times the wheel radius, which would be an R1. This would be wheel radius. This is not R1, we'll call this RA. Just try to give some different values. I'll call some of this omega A. That's the rotation speed of the wheel. And then V2 is going to be equal to omega b RB, where this is the wheel radius again multiplied by the angular rotation of that wheel. Okay, so you can get a lot of different things out of this. So if just by changing your V1 and V2 values, you can actually change your R1 and R2 values, which is kind of interesting. R2 minus R1 will always be fixed because you will always have this value, but you can increase R1 and R2. So if you want a really, really broad turn where R1 and R2 are very large, your two velocities will be really close to each other. Okay, you want a really, really tight turn where this turn is really sharp. Your V1 and V2 values will be somewhat different. And in fact, you can even get it where one of your speeds will be negative. So like, let's say you want your vehicle to be turning about at center here. If this one's going at a positive speed, this one's going at a negative speed, it will actually turn, and it breaks the math here, which is kind of interesting because you end up with a negative radius. But the difference between the two radius, R2 minus R1, will always be the same. But you will be able to still get that turn because if your velocity goes negative, your radius goes negative. And the moment that happens, you're now turning. This is where zero turn motors often will operate, is one wheel will go forward, the other wheel will go backward. Okay, so this is really the relationship that you end up with. Well, this one, your omega doesn't matter as much. This is your rotation about some fixed point, which acts as the center of rotation for your entire turning motion. But this is really where it comes from. The velocity of one wheel over the radius to the center of the curve is equal to the velocity of the other motor divided by the radius from that wheel to the center of the same curve. Okay, so kind of a lot of information. Please feel free to respond with questions as you have it, but hopefully this gives you some of the math behind how to control the steering, how to do that. If you were to have a four motor system, these two motors likely will be powered with the same exact power. You would only end up having two independent wheels. You can have an off-road application there, and there's no need for independent control. You can get into talking about slip and those kinds of things. That's really complex. Where you guys are at, I think that's a little bit more challenging when you start having when you have to talk about differentials and those types of things to ensure that you're maintaining contact. Because technically you would need a differential between these two wheels and a differential between those two wheels, and it's just a pain in the butt. The other side is, if you want to only have a one motor operation, here you would have likely a broken axle up front. This would probably be some kind of a wishbone operation, wishbone suspension. And then in the back you would have a solid axle that would connect to both of your wheels. Try to get out of the way of my drawing. You have a solid axle and you're powering this one axle. And then what happens is you actually have to have a linkage that comes off here, goes across and connects to both sides. And then you have a servo motor which would turn one way or another, and it would force the wheels then to spin, to turn one way or another. This is slightly more complex. It gets into more realistic vehicle dynamics. If you really want to go that route, I can record a second video for you, but that second video would probably be just as long as this one, if not longer, because turning can be a little bit more challenging in this regard. That said, some people like to do it because it is a much lighter vehicle with only having one powered axle and having the steering linkage, and the steering linkage itself looks pretty cool, and you can, oh yeah, I can remotely turn the vehicle. That's nice. But if you would prefer to do the one motor rear axle with a separate servo motor to control steering, just let me know and I'll give you another video. Hopefully this has helped. I'm going to go back to my alien captivity, so